the dawn of orbital computing, moving data processing into space. While the concept of massive data centers orbiting Earth has long been a staple of science fiction, the industry is moving from theory to reality. Rather than building supercenters in space, the first wave of orbital computing is focusing on edge processing, the ability to analyze data right where it is collected, rather than waiting to beam it back to Earth. The current state of orbital infrastructure, the leading player in this niche, is Canada's Kepler Communications. Unlike the massive, centralized data centers envisioned by giants like SpaceX or Blue Origin, Kepler has deployed a distributed network. Their current cluster consists of 10 operational satellites linked via laser communication, approximately 40 NVIDIA Orin edge processors distributed across the constellation. This setup is designed for efficiency rather than raw power. Kepler's strategy focuses on inference using AI to make quick decisions based on existing data rather than the massive, energy-intensive training of large language models. A strategic partnership. Kepler and Sophia Space. Kepler recently announced a partnership with Sophia Space, a startup aiming to solve one of the most significant hurdles in space computing: thermal management. In the vacuum of space, getting rid of heat is incredibly difficult. Traditional active cooling systems are heavy and expensive to launch. Sophia Space is developing passively cooled space computers to mitigate this. The partnership will serve as a critical, de-risking mission. Sophia will upload its proprietary operating system to Kepler's satellites. They will attempt to configure and run software across 6 GPUs on 2 separate spacecraft. This test is essentially the space version of standard terrestrial data center operations, proving that software can be managed reliably in orbit. Why orbital edge computing matters? The immediate value of this technology lies in speed and responsiveness. By processing data in orbit, satellite operators can bypass the latency of downloading massive files to ground stations. Defense and surveillance. The U.S. military is a primary driver for this technology. Systems like synthetic aperture radar, SAR, generate enormous amounts of data. Processing this data in space allows for near-instantaneous detection and tracking of threats, such as missiles. Satellite networking. Kepler aims to act as a service layer, providing networking and processing for third-party satellites, drones, and aircraft. Resource efficiency. By using distributed, lower-power GPUs that run constantly, Kepler avoids the massive power surges required by centralized superchips. The long-term outlook. Space as a solution to earthly constraints. The shift towards space-based computing is being accelerated by growing tensions surrounding data centers on Earth, increasing regulatory scrutiny, and local bans on data center construction recently seen in Wisconsin and discussed in the U.S. Congress are making orbital alternatives increasingly attractive. While large-scale, high-capacity data centers are likely not arriving until the 2030s, the groundwork is being laid today through specialized, distributed networks that turn satellites into intelligent, thinking machines. Conclusion: the first era of orbital computing will not be defined by massive, centralized hubs, but by distributed, edge networks that process data instantly in space. As terrestrial data centers face increasing regulatory and environmental hurdles, the move to orbit offers a viable path for the next generation of high-speed, high-demand computing.